And now, Mr. Cosmos DB from the Seattle of United States.
No, well, I used to live in Seattle.
Yeah.
I live in.
Aren't you moving there back?
I am moving back, so I guess I will be a Seattle resident. So I lived in Seattle for over 20 years. Before that, I used to live in Southern California in a little town called Laguna Beach, which was nice, expensive, but back in my 20s, I had a lot more disposable income, right? So, you know, family, wife, kids, all that stuff makes it worse. So, yes, I live in California, but I will be a future Seattle resident again. I'm Mark Brown. I'm a program manager on the Cosmos DB team. And I'm going to talk to you today about how to model and partition data for NoSQL databases to get really high scale out of them. I want to ask some questions here, but I've been told I need to show this slide first. So we've got Andreas, and then Sakari, and then who's the and then Magnus in there. So by the rules of Inception, this talk will take about 600 years. Okay, I got like 60 minutes or less. So I have some objectives here, but I want to understand my audience. So who here has used NoSQL database like Cosmos or even Mongo or Cassandra? Wow, okay, that's a large group. Like successfully in production? Hands? Successfully in production and happy with performance and cost. Okay, there we are. Yeah, you're in the right place. I'm going to try and help you out with that today. Who here uses SQL Server? Like all day long, right? Or MySQL, right? So, okay. This talk is really designed for people who have spent their entire lives or careers working with relational databases like SQL Server, MySQL, Postgres, doesn't matter. What we're going to talk about is how to design for this type of database, a NoSQL database. And we're going to apply this to a real-world scenario. And my hope is that after this, you'll understand things like why do NoSQL databases exist? Like, why did they even create them, right? What's the point of having these things? And then understanding kind of, all right, well, how do I design for these things, right? Now that I understand what they are and why they are, how do I design for them to make them both really fast, efficient, and cost-effective? So that's what we'll do here in this session. So I work for Cosmos DB, and you may be asking, well, what is Cosmos DB? And officially, it's Microsoft's NoSQL database on Azure, or distributed NoSQL database on Azure. Now, NoSQL is kind of a loaded term. And what we really mean by that is that Cosmos is both non-relational, as databases go, and horizontally scalable is another key aspect of that. Now, let's break it down like a bottle of Mintu for you here, right? What does horizontal scale mean? Well, for small databases, it doesn't really mean much, right? The notion of horizontal scalability or scalability in general doesn't really matter until things need to scale, right? What's different about us is that with a relational database, how do you scale? You provision a bigger box, don't you? Right? So that's how you scale. You scale up with a database like SQL or MySQL, right? A database like Cosmos does something quite different. It creates more little databases for you to store your data in. And this is really an advantage because what it provides you is essentially infinite storage capacity. I mean, whatever's available within the region or data center that you're working in is potential for storage for your application or your service in there. Another key aspect of this as well is because of this horizontal scalability nature, like each one of these things is essentially a different server, right? Or it's kind of a fraction of a VM within there. Well, not only do you have storage with that, but because that little piece of compute also has CPU, memory, and IOPS and all that stuff, you also have additional power, throughput, to be able to access that data. So you get really unlimited throughput or scalability for your applications. So let's talk about the non-relational aspects of this. When working with relational databases, you have the ability to be able to define things like constraints and put joins on things. Databases like Cosmos, we don't do that type of thing. You don't have the ability to be able to, well, we do have joins, but they're not across entities or across what you might think of as a table with a database like this. And why? Well, because Cosmos is horizontally scalable, right? The idea, in Cosmos, it's essentially like a shared nothing architecture within there, right? So data gets put on these different servers, but these servers don't know about each other, right? And so if you wanted to do something like that, enforce these types of constraints or perform joins across things like containers or partitions or anything, you're essentially creating or having to use things like distributed transactions. Now, that's not really always a good thing in terms of either performance or availability, right? Because you're doing something that's going to go across a wire or across a network, put locks on that data, and then wait for that transaction to finish before you can do anything else. This is very common in a SQL Server world where you have that ACID consistency, but you kind of need to throw that out the window. There's other ways to maintain consistency with data you write, right? Cosmos uses a quorum mechanism to maintain that consistency within its replicas or data set. But this is kind of fundamentally different. We want to avoid doing distributed transactions or putting distributed locks on data because of that impact it can have on availability and basically performance in there. And fundamentally, Cosmos is a database that's designed to provide predictable performance, right, and high availability. Those are kind of the two key features for a database like that, or for why you would want to use a NoSQL or distributed NoSQL database in the first place. That's kind of why they were created, is databases like SQL or MySQL or Postgres run issues or have issues when you get to a certain size. And they can also get to issues with performance as they grow exceptionally large as well. And these are the types of things that you can avoid when you use this type of database, provided you can model your data and understand a partition strategy that's going to help it scale. Okay, so at this point you may ask, well, geez, Mark, is Cosmos even a good database to use for my relational kind of workload? And the answer is absolutely, it sure is. Most workloads that are built and use a database like Cosmos, in fact, most workloads in general have data that have relationships defined between them. The trick here is you need to understand kind of different techniques used to implement things like relationships. There's different techniques and a different mindset and things you need to be aware of within your workload that's super important to know early on when you're designing it, because the approach that you're taking is going to be fundamentally different. The last thing I want to say too is read the damn docs. This is not intuitive stuff, the stuff I'm going to show you. 9 times out of 10, the questions I get from people is right there in the docs, just look it up. So, but fundamentally, the best practices you're going to think about, or when you try to design a data model, just chuck it out the window. This is not an intuitive process. It doesn't translate well. You can even basically end up implementing any patterns if you don't think about what you're doing in here. Okay, so we're going to do basically an example or a process here where we're going to take a relational database that I think most people know. Who knows AdventureWorks? Right? Everybody. If you use SQL Server, everybody knows AdventureWorks. So we're going to take AdventureWorks. This is a slice of it, AdventureWorks 2017, and we're going to remodel this for a non-relational database. So let's look at some of the entities we've got in here that I'm sure you're all familiar with. We've got our customer table, and then we have a customer address table, and we have a one-to-many relationship with that. We also have this separate table for the password, which is going to store a hash on the salt for the customer password in there, and that has a one-to-one relationship to our customer table there. We've got some product tables. So I've got a product table itself that, of course, has categories for all of those products that they live within, and there's a one-to-many relationship for that. We also have product tags. So we have a different relationship here. We have a one-to-many from product tag to product tags, and then there's a many-to-many relationship, right, from products to tags, because tags can be associated with multiple products. And last, we have sales orders. So I've got my sales order header table here, and then it has a one-to-many relationship to my sales order detail via the sales order ID. This is essentially kind of the cart for my e-commerce platform here. Okay. Let's see, did I miss anything in here? Where's my mouse? Yeah. Okay, one last thing I do want to say. When you're designing a model like this, what's the thing that matters most when you're designing for a relational database? Come on, who knows what, right? Third noble form, anybody hear that before? Right. What are you optimizing for? Storage. right? What are you trying to do when you normalize your data in your model? You want to eliminate duplicates, right? You want to separate entities into their own tables, right? Why do you do that? Well, I can tell you why. Because when relational databases were first designed or proposed in 1970, believe it or not, relational databases have been around for over 50 years. How much do you think a megabyte of storage cost in 1970? You guys are really quiet. Do I have to give you all the answers? Hey, did I mention there's a coaster in it for you if you say something, right? You could put your Mintu on this. It's expensive. In 1970, a megabyte of storage was like $2,000, right? I've got a phone with a terabyte of storage in it that basically costs the same amount of money. So the whole point of normalizing data is to optimize for storage, right? Well, fast forward 52 years, that storage is really cheap now, right? And cheap compared to what? Cheap in relative terms to compute, right? Because your data is useless unless you can write it and read it. So it takes compute to go do that. So this type of database, and what you're going to learn here, is we're going to take a different approach. And we're going to optimize for the compute that's used to read and write data from your database, not the storage, right? So all these things I'm going to talk about are going to be how that matters. And as you think about compute, what does that translate into? Really, it means kind of what operations are you going to do with your data, right? What are the things that are going to happen with your data, particularly with high concurrency? Those are the things that really, really matter because that's where you're going to need to scale, right? So when designing a data model for an application that's going to use Cosmos DB, we have entities, we start with those, but the most important step to begin is understanding the operations for that application, okay? So here's all my entities that I've got kind of broken out. For customers, I need to create a new customer. I need to edit one. I need to get one. Product categories, I'm going to have the same. I'm going to create and edit. I also want to list all product categories in this application. And I want to do the same with tags. I want to create and edit tags. I need to list my tags. For products, I want to create a product, obviously, edit. And then I want to list all products within a particular category. So the way I've designed my e-commerce application is I go and navigate by categories, and then I click on a category, and I see all the products for that category, right? Not only that, but I want to see the name of the category on that page, and I want to see all the tags for each of the products, okay? Last, I need to create a sales order. Obviously, this is e-commerce, and nothing's getting done unless somebody's making money. I also want to list all sales order for a customer. This is a very common operation, right? If you go into, say, Amazon or the Finnish equivalent of Amazon. Is there a Finnish equivalent of Amazon? No? Okay, so Amazon or your favorite e-commerce application. What do you do sometimes? I go in and I look at old orders because I want to maybe buy something again. Right, so that's another operation I want. And then I've got a last one here. I've kind of thrown a little kicker in here. I want to query my top 10 customers and do it by the number of sales orders. Let's say I want to give them like a little gift card or some bonus every month. Like, hey, thanks for being an awesome customer or our best customer. Here's, I don't know, 20 euro for you. Okay, so those are the operations. Here's our data model. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 tables in here. And we're going to take these 9 tables, and I'm going to remodel this for Cosmos, or for a distributed NoSQL database, and it's going to be super fast, super efficient. It's going to knock your socks off. Okay, let's get started. So let's start with the customer entity here. First thing, what operations am I going to do on these tables? I need to create a customer, I need to edit a customer, and I need to retrieve a customer. Now, given that Cosmos stores data in a JSON format, one of the first things we would do is we would try to define this in JSON format in here. Now, remember that these data with Cosmos, like we don't support things like joins, right? So how do you manage this? Well, you can embed that data, right? JSON can support hierarchy, right? And can support arrays within that sort of data there. So what we can do is we can take this data from those 3 tables and then embed it. Within there. So I've got my customer table within here. I then have, since I have a one-to-many relationship between those, I'm going to have an array of addresses within there. And then I've got my password table within there. So I'm just going to add that basically. It's just going to be like an object within my database. Okay, so at this point, some people will ask, well, when would I embed data in a document if I'm modeling relationships versus when would I reference that, right? Maybe add that as a separate row in there. And there's actually some really good hard and fast rules for when you would embed versus when you would reference. You want to embed data when there's a one-to-one relationship, right? Or maybe one-to-few. Now, you may ask, what does one-to-few mean? Don't you mean one-to-many? And I do mean one-to-many. The difference is that a one-to-few relationship is a bounded kind of relationship, if you will, right? Like addresses, you're going to have maybe more than one address you want to ship to, right? Like I want to ship it to me, I want to ship something to my mom or to my brother. But you're not going to have an unlimited number of addresses within your document, right? It's a bounded array. So it's a one-to-few is the way we kind of coin that. The other really key aspect, too, is that the data you're modeling and embedding within the same document is queried or updated together. It's going to be accessed at the same time. Remember, what are we optimizing for? Compute. So if it's queried together or updated together, that's an awesome piece of data that you should embed with that other, whatever, entity or data that you're using in there. Okay? When would you reference data? Well, one-to-many's relationships, especially if it's unbounded. And I'll tell you why this is important a little bit later. But this is one where you definitely, and I see a lot of customers and people do this, is they just have these unbounded arrays in their documents. And they're like, hey man, I just got like a, what was it? Is it a 409 when I tried to update this thing? What's going on? And the problem is that they've got too much data inside that document. The other scenario too, where you want to reference is many-to-many relationships. That's when you want to reference as a separate row, not embed inside the document. And then the last one is if the items in question are queried or accessed independently, particularly if they're updated independently. And in particular, the most important is if you have an asynchronous access pattern for your data. I see this quite a bit as well. Cosmos as a database, when you do an update on your data, it's going to send back the entire document, right, in your payload there. And if you're doing high concurrency updates on just one or two properties, that's an expensive operation. You could make that much easier if you shredded that document and made two out of it. And then you have one document that's largely static with those properties, and then another one that's quite a bit smaller where you're doing high concurrency updates. That's going to be far more efficient than if you have to shuck that entire document back and forth, particularly with high concurrency. I will point out we do have a new feature, relatively new, kind of technically called Json Patch. But basically what it does is it allows you to update, do a partial update on that document. Nice thing about that is that it reduces the payload, so that's going to reduce the number of resources that's consumed on the client, your client, the one that's running our SDK. The other thing is it's got some other really kind of cool features to it as well. But on the server side, it's not really going to save you a ton of money or a ton of throughput or RU on there. So I just want to point that out. So, okay, so here's our first entity. We've got one-to-one relationships in here, and we've got one-to-few relationships in here. So we're going to embed everything into a single document. Okay, so we've got our first entity. Now, when you create a container in Cosmos DB, it asks you for something called a partition key. Well, what's a partition key? Well, remember earlier when I said that Cosmos DB basically provides this abstraction over containers or partitions within your data across these kind of physical servers that it's storing its data on, right? So when you're storing documents in Cosmos, you have to, they get written to these different physical servers, right? And you may be thinking, well, how do I control where my document is getting written to if I don't have a single database that I'm writing to all these different ones? Now, that's actually something you don't need to care about. What we have within Cosmos DB is this notion of logical partitions. So think of it this way. The piece of compute that you get and keep adding on to, we call internally a partition, right? It's really a little slice of computer, a little VM within there. With our design within Cosmos, we've implemented this kind of layer over that we call a logical partition. And the idea there is to provide kind of the same feel for that, or just, how do I put this? How do I get this? All right, let me put it this way. Within Cosmos, we run on multiple generations of hardware. Some of it has less storage than others. To provide kind of a uniformity to that data, we define this thing called a logical partition. And the size of that, well, I'll talk about that size of that there. But really what I want to say is you don't need to care about logical partition. Well, you do need to care about logical partitions, but you need to care about where your data is physically stored within there, right? You're going to use this thing called a partition key. And partition key is going to be a property within your data, right? It's something that should be innate to the data that you're storing within there. So here I've got a partition key of username. So within the logical partitions I've got here, I'm going to have a logical partition with username Andrew, and another one with username Deborah and Tim and Mark and Luis and Theo. And those, that's going to control, if you will, how your data is written into Cosmos within there. Okay, so there's two things I want to point out here. One, there's some constraints that you need to keep in mind when you're modeling your data in Cosmos. First is the maximum size of a document within Cosmos is 2 megabytes. Now, remember earlier when I said you want to avoid unbounded arrays when you're modeling your data? This is primarily the reason, is you're going to end up hitting this 2 megabyte limit. The other thing I want to point out too is that as you increase the size of your documents within Cosmos, the cost of the RU, or the throughput necessary to process it, doesn't grow linearly with the amount of storage in the document. It actually grows at a faster rate. So the bigger the document, the more expensive it's going to cost. In some cases, once you start getting out of about like the 500K range, it may be actually cheaper to shred the document into 2. Right? Now, that'll help in a couple of ways. One, if you do updates, you don't have to shuck the whole payload back, right? So that'll help with that. But just on a per operation basis, for that same set of data, it may be less expensive for you to shred that document. And also avoid unbounded arrays. And then the second limitation I want to point out is for a logical partition, that maximum size is 20 gigabytes, okay? So you need to make sure that when you're designing a partition strategy around your data, right? So all of my data in each of these logical partitions is going to be probably stored on different physical servers. You need to make sure that you've got high enough cardinality with that partition key that you don't blow up that 20 gig storage limit within there, okay? All right. Now, when you provision a container in Cosmos, you're going to pick that partition key. You're also going to select the amount of throughput that you want on that container. That throughput controls, if you will, how many physical partitions, how many of those different physical servers we're going to provision for you in the back end. And when we do that, the throughput, right, that essentially that's the kind of the compute necessary to run that partition, is spread evenly across all of them. Now, there's some implications for this. First, you want to make sure that you design a partition strategy that's going to spread your data evenly from a storage perspective. If you don't, let's just go back to the example of like username. Like say Andrew is really, really popular, and I know he's got lots of documents in his logical partition, and the other people are not so popular in there. You're going to end up with a scenario like this, where you've got one logical partition that's got all the data in it, and others with very little, right? And this is what we call canonically kind of a hot partition within there. And this is definitely something you really want to avoid for all the reasons I just stated earlier. Same thing goes for requests as well. Take the storage aside, but if say Andrew or Mark has lots of requests going to it, then you end up kind of a similar issue there, where you end up kind of with this hot partition that's going on there. Now, you may ask, like, why do I care about this, or why would it matter, particularly from a request perspective? And keep in mind that this throughput that you provision for that container, you're paying for, right? It's like a VM, right? You wouldn't provision like a ginormous VM and play solitaire on the thing, right? Because that's a waste of money, right? And you want to be efficient in how much resources you're going to provision for your account or for your container within Cosmos. So if you've got a hot partition from the number of requests that are going on within there, you're not utilizing, first of all the throughput that you've provisioned, right? It's just not there. You're only getting a slice of that because you've got multiple physical partitions in the background. More worrisome is that you have partitions that you're paying for, but you're not using, right? Again, it comes back to the access patterns that I talked about earlier, right? Understanding those access patterns, particularly those that have high concurrency, is going to matter, right? And that comes together with the storage on that. Now, how do I describe this? I mean, let me go through a slide because I'm kind of riffing, if you will, on this. So I talked about the hot partition for the storage and for the throughput on there. I had one more point I was going to make to you guys. It'll come to me. So, long story short, this is what you want to see from both a storage perspective and a request perspective within there. It goes back to the access patterns. Like, the thing that matters in how you get to something like this is having a really solid understanding of the access patterns for your app. Now, what does that mean? That means I need to know all of the operations that are going in. That means I need to know how users get into that part of the application. That means maybe I need to talk to guys like my UX designer and others who are working on designing and building this application or service so that I can understand fundamentally, how is this app going to behave? If I click on this, how many things go on in the background? Now, if I multiply that by X number of users, how many times does that happen in the background? What's the likelihood that I'm going to get that number of users? You have to even go through a capacity planning type of exercise when you're thinking about designing these types of things. It's a lot to take in, and it's a heavy burden early on when you're designing an application or a database with Cosmos. But to get to a point where you can achieve kind of this infinite scale, these are the types of considerations that actually matter a lot when you're designing a database like Cosmos. Another thing I'll say too is don't be afraid to iterate. This happens over and over and over again. I see customers, they go in, and they may understand all of these things, right? And understand their workloads and the behaviors of these things. But you know what happens with apps that you design and you put into production? Is customers sometimes use them in ways you didn't realize, right? And the assumptions you had early on are gonna be like, oh, I didn't see that coming, and you're gonna have to redesign. And so being comfortable with iterating on your design over time, particularly through the development stage, but even into production, there may be needs where you need to go and make changes and migrate your data into a new container with a better partition key. One more thing I want to say. In a write-heavy scenario, when you're designing your application, the thing you want to do is you want to distribute those writes across all of those partitions as much as possible, right? Because what do you want to avoid? You want to avoid this that's going on. So say I'm in like an IoT scenario or something like that. What would be a good partition key? Was date a good partition key? Who thinks date is a great partition key for any scenario in a write-heavy workload? Good. Who thinks it's a bad idea? Yeah, why is that? Come on, you get a coaster. Why is date a bad partition key in write-heavy scenarios? That's correct, because today is always hot, right? Always. You cannot get away from it. You've got to use something else. Something maybe like device ID is good, right? Because it's going to be unique across all the devices, and presumably all your devices are emitting data at the same rate, right? That will get you back to something being smooth. Now, let me go and talk about reads, because another thing you need to solve for in applications is reading data, right? So if I have my whatever collection here, and I'm using username as my partition key, if I have a high concurrency query like this one here, where I'm going to select star where C equals username mark, and what's going on with my thing? Uh-oh, battery dead. All right, here we go. Oh no, what's going on? There we go. Yeah, sure. Here, my username is my partition key, right? And that, now it's working again. So that's good, right? Because Cosmos knows exactly where to route my query, right? That's efficient in terms of design, especially for high concurrency queries, right? What if I have a query like this? What do you think happens to that query? That's right. It doesn't know where to go. So what does it do? It dispatches to all the partitions. And this is something what we call a fan-out query or a cross-partition query. You can have cross-partition that's not fan-out, but you can have true fan-out where nothing in your query is going to help it find the data that's in there. So what does it do? It dispatches to all of your partitions, and it's going to search for all of them. And this is very expensive because each of those is going to consume throughput on each of those partitions. It then needs to take that data and then put it back together and then ship it back to you, right? So these are very expensive. You want to avoid these things at all cost. Okay, hold on. Last thing I want to say. So you understand, right, designing for the read heavy, what do I want to do? My objective is to make sure that for high concurrency queries, my data is sitting on a single partition, right? But what if I have an IoT scenario like I just said? Because I just said the opposite before, right? What was my objective there? I wanted to spread it out, right? And now I'm saying, no, you want to keep it together, right, for the read-heavy workload. Well, what if I have both? Does that ever happen, where I have to write a bunch of data and then I have high concurrency reads? Yep, it sure does, right? In lots of applications. In an IoT scenario, where I'm partitioning by, say, device ID, there's no way that I'm doing high concurrency queries on a device. It just doesn't really happen. I'm probably going to look at it by, I don't know, depends on the scenario, maybe a building ID or my floor or by customer or something. It's not going to be the device. It's going to be some other value, some other property within there. So how do I solve for that, right? Mark, you're telling me that I need high concurrency for writes, but I need this for reads. The answer is just create another container, right? We don't care about duplicating data. And in this scenario where you've got high concurrency writes, very high volume of writes with high volume reads, you need to solve for both, right? And since we don't care about storage, we're gonna use, well, something called change feed, and I'll show you that in a few minutes. And we're going to copy that data. So everything that's written or updated into my first container where I'm ingesting all that IoT data, I'm going to then copy into a new container, and I'm going to give it a new partition key, whether it's name or building or something within there. Okay. That's a lot of heavy concepts. You guys okay? Everybody all right? I'm going to show some code. I thought this was going to be a code-free day until the last session, and then I got beaten to it. But the rest of the session, I'm going to go through, I'm going to model AdventureWorks. I'll show you some, and then I'm going to do lots of demos. So this is going to go back and forth really fast, okay? I'm going to show you some code. I'm going to show you our SDK. And I'm going to go through, and I'm going to model this data, and I'm going to show you how it works, okay? So we just learned a whole bunch about partitioning within Cosmos and design stuff within Cosmos, and hopefully that's all sticking to you. What are we going to do for partition key? Well, let's look at our access patterns, right? This always comes back to the access patterns. I got to create a customer, I need to edit a customer, and I need to retrieve a customer. Which of these three operations do you think happens with highest concurrency? Retrieve. And how am I likely going to want to retrieve the customer? Let's say I'm logging in. What am I going to use? Like a username or an ID or something that's going to be unique, right, within there. So I'm going to call it ID here. It could be anything, but it has to be something that's unique within there, right? So I'm going to use ID as my partition key for my customer container here, okay? Now what that does is that fundamentally creates a logical partition for every single customer within that container, right? Remember the logical partitions, those are the things that your data goes into and you get 20 gigs of storage, right? Well here, I'm going to have logical partition for every customer, but it's only going to have a single document in there. Now, I sometimes hear, hey, is that okay? Can I have like 1 million or 1 billion logical partitions within a container? And the answer is yes, right? It's just a logical construct, these things like logical partitions. It doesn't change or matter really in any way from a performance standpoint. The way you can think about using something like ID as a partition key is that it fundamentally turns the container into a key value store, right? Because really the only thing you can do in that sense is just, if you want to do an in-partition read, is just do a read in there and use the partition key as the ID, and then pass both ID and partition key when you're reading your data within Cosmos. Otherwise, if you ran a query in there, what's going to happen? Cross-partition, right? And that's something you want to avoid. One other thing I want to talk about too before I get to a demo is don't feel like when you go and you design a database in Cosmos and you do all this testing and stuff like that, and you're like, oh, these queries are great, they're fine, they're fine, they're fine. That doesn't mean anything in Cosmos. If you want to design for scale, guess what? You got to scale it first and then test it and see how it works. So you've got to load test these things using tools like Bogus and others that you can use to ingest tons and tons of data, put load under the thing, and then measure, right? You've got to get it out to a point where where it needs to scale, and then measure the performance that's going to happen within there. If you create a database and you're, let's say, less than 50 gig, because that's the maximum size of a physical partition, the data that you get back is going to be meaningless. You need to scale that thing out to a greater extent. Then load test and measure, and then you can tell. Did I make a good design? Okay, so let's do some demos. How do you guys feel about that? No? You guys don't care about demos? All right. What's wrong with my mouse now? Are you looking at the right thing? Okay, good. So I've got, I've got my Cosmos account here, and I have 4 databases in here, and each of these represents kind of a different iteration as I go through and I model my data in here. So my first one, V1, I've got all the different entities, all 9 of them, that came straight over from AdventureWorks. I've got customer, address, password, product, blah, 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 okay? And as I go through, I've got another one here with customer, and you can see I'm missing customer address and customer password. Why? Because I've modeled it within my customer container. So to understand why modeling data this way matters from a performance perspective and from a cost perspective, let's take the original, the V1 here, and run some queries if I want to go and fetch a customer as they come in. So here I've got a query, select star from C, where CID equals this customer ID that I'm going to use for the rest of this demo. And here you can see I've got data within here. Here's a customer, and partitioned by ID. And you can see, whoops, first name, last name, email, address, phone number, all that stuff that I showed you earlier, okay? So let's run the 3 queries we would need to run to get our customer. So I've got this one here. I need to run this. And that's, yeah, fine. Query stats. How much did this thing cost me? 2.83 RU. Okay. Let's go do the second one. So this one is going to go and grab address data right here. So let's run this guy. Execute. And what happened? Where's my... There we go. And this one, that's more expensive. That's 11 RU. So we're like 14 RU for those 2 queries. I got one more. I got to get my password. Yep. And that one, about 3 RU. So 14, another 3 on there, about 17 RU for that one query, right? Not only that, but I had to dispatch 3 different queries over the WAN 3 different times, right? So that adds latency and cost. Now, let's look at it. Here's my V2. Here's my customer within here, all right? And I've modeled all this together. So I've got my customer in here. Here's my address within there. And then there's my password within there. So let's run a query on customer here. Portal, there you go. And I've got my customer in here that came back. More importantly, the cost of that query is just that 3 RU, right? So order of magnitude less expensive, plus 1 operation, not 3, right? Because we're optimizing for compute here, right? Okay, so that's the portal. Let me show you how you do this in Visual Studio. So I've got a little app running here. That's this one here. I'm going to run some demos, and I'll show you the code. that we've got in here as well. So here's how you do a query within there. So I need to get a reference to my database and my container. So there's my customer container. Oh, and that's going to, yeah, v2. And there's my customer ID that I use in my query. Here's a little query. This should not be too weird or different for you to look at. I'm going to create this get item query iterator, send it a query definition, a parameter, and then request options. I want to pass my partition key. Super important every single time. Pass the partition key in your query. If you don't, guess what? Cross-partition query. One caveat, you can not include it, but if it's in the where statement, we'll sniff that out and still run that in the partitions that you have within there. But as a best practice, I like to put it in there because it better documents the code that I've got in there. Okay, so I'm going to run this query, and then I'm going to iterate through it, and I'll print out the request charge in there. So I'm going to run number A there. Here's my customer. Quote for a single customer coming back here. Destiny Peterson, there's the address, there's her password, and there's my request charge, right? The 2.83 that I showed in the portal, right? So that's okay. One thing that a lot of people don't realize is that if you are using ID as your partition key, you can also use this other operation we call a point read, right? You can also do this when you're looking for other data, provided you know the partition key value and the ID for the data you're looking for. And let me show you that, because this is quite efficient as well. So here's my same customer ID, and I'm going to call this function called read item async. I'm going to deserialize that into my customer object here, and then I'm going to pass my customer ID, right, which is the ID, and then for my partition key, pass that same value, okay? And then I'm going to print that out and the request charge. So remember before, how many RU did we have for that query for a single record? It was 3 RU. Let's try a point read and see what happens. So there's my same data, but my request charge is just 1 RU, right? So I've gone from 17 RU down to a single RU by modeling my data in a way that's efficient for a NoSQL database, and then also this operation where I'm just looking up a single record. If I know the ID and the partition key, I can get it this way, right? This is the most efficient operation you can run in Cosmos, is a point read within there. And where you have high concurrency operations, I would strongly push towards being able to do point reads on that data because it is so efficient. Okay. Let's go back to slides. This thing, I think it's working again. Okay, next up, let's work on products. First, I got product category. I'm going to do the same thing I did with customers. I need to, translate that into JSON. Within there, I'm going to put that in its own container. I'm going to call that product category. But I have to pick a partition key for that thing. How am I going to do that? I'm going to look at the operations again. I'm going to need to create a product category. I need to edit a product category. And I need to list all product categories. So what do you think is going to be the high concurrency operation out of all of these for product category? It's going to be list, right? Well, I can do a select star from C out of this container and get all my product categories. And that's probably going to be efficient. Actually, in fact, I know it is, right? Because there's not much data in terms of product categories within there. But I'm going to do something a little different here. And this may look weird to you at first as I go through this, but believe me, there's a reason why, and it's actually something you'll think that's very cool when you're done. I want to make this an in-partition query, okay? So I'm going to add a new property to this container, and I'm going to call it type. And I'm going to give it a constant value, and I'm going to call it category, okay? Whoops. And now, when I run queries on this container, they will be efficient always, no matter how many. Well, that's not true. It'll be efficient for product categories within this use case, and the reason is you'll see why later. So let me do another quick demo on product categories. So list all product categories. I've got my product category container, select star from C, where C equals category, create my partition key, passing in that static value, string, category, and then I'm going to iterate through all that and show you the request charge within there. Okay, so list all product categories. Whoops. Oh, I just put a C in my code, which made Visual Studio very mad. Okay. Oops, there we go. So categories coming out here. Got the ID, the name, and then the type, obviously, coming within there. Okay, and then request charge. Where is it? Man, a lot of categories. About 4 RU. So that's not bad. But honestly, without a partition key, that'd be okay, too. However, you need to define a partition key for your container. In this case, I'm going to use this type thing, put a category in there, and then use that. And that'll keep it in partition. But the real reason why you're going to care about that, I'm going to show you in a little bit, okay? Just trust me. Okay. Next, let's do product tag here. So same process. I'm going to put that into JSON, create a product tag container, and look at my operations, create and edit. I'm going to list all product tags. It's going to be my high concurrency. And I'm going to apply that same technique I used earlier. And I'm going to create a type property, and I'm going to give it a constant value of tag within there. Okay. Next up, let's look at product within here. So I want to look at the relationship I've got between product and product tags. Remember, we've got a many-to-many relationship that's going on with here. And I need to access the product tags, meaning I want to display them when my products appear on that page. So I need to be able to query that in a high efficiency way and return back my product tags with the product that's within there. Now, I could do this in kind of one of two ways. I could store the product info in my product tags container, or I could materialize those tags and denormalize it within my product container. So that's what we're going to do. Because there's fewer tags per product than there are product per tags, it makes more sense to materialize that, right? I'm denormalizing, materializing that data into my product container here. And remember, there's a one-to-few relationship, right, between product and tags, right? It's not an unbounded relationship. So I'm okay embedding tags into my product container here, right? This is a good candidate for embedding. So this is going to be the structure of my new product container here. So I'm going to have products that I showed earlier, and then I'm going to have an array of tag IDs as well. So next, need to figure out a good partition key. So I want to create and edit a product, but those are low concurrency operations. The one I'm going to be running the most is going to be listing all products from a category with the name of the category and the tags. So we need to run these queries here. I need to select star from C, where C category equals category A. And then what you're going to have is within every category, you're going to have all the products within that category there. So that's good. That's going to be when I click on the product category, single partition query, high efficiency, all good within there. So what do I do about the category name and the tag names, right? Because I want to display those within them, but they're sitting in their own container. All I've got is the IDs within here. Well, I have to run a bunch of queries to get that, right? So I want to first run a query against my product container, right? So I want to get all the products for category A. I need to then go get the name of the category, right? So I then got to go run another query on my product category container. And then I'm going to have multiple products come back, and each of those is going to have its own set of tags associated with it. So depending on how many products I get back, I'm going to have to run subsequent queries to go get all the product tags for all the products. Now, you may be saying, hey, just join the thing. But we don't do joins, right? We don't do distributed transactions, potentially where you would have data in different containers or in different partitions sitting on different physical pieces of compute, right? So what am I going to do? Well, I'm going to denormalize that data, right? Again, I'm going to embed the name of the category and the name of the tags within the table, or within the, the container itself. This is going to help reduce the number of round trips that I've got to make, particularly if I don't know how many I got to. If I got to iterate through a result set to go run more operations, that's a bad idea, right? Just no matter what, if you're using this type of database or not, it's a bad idea. You want to model your data so that it's ready to go as the user needs it within your database. So we're going to denormalize and then optimize our data for that. So here I've got my new product category, or my new product container, product category ID, right? Because that's how I'm looking them up. And within there, I've got my category name now embedded within there, and then the tag for each of the tags that's within the array there. So by doing this, we make sure that basically we can retrieve all the data for that category in just a single request. Okay, so let's show you how that looks. How am I doing on time, by the way? Are you serious? Holy crap, we're gonna forget that demo. I'm gonna keep going here. All right, it's an awesome demo, I'm kidding. It's not, it's just a demo. I'm gonna show you all the product categories. So this is great. So now, you know, what happens though when I change a category name, right? I've got to reflect that and keep that in sync with my product container, right? I've created a problem here, right? And I know as a SQL developer, when you denormalize your data, you always create this secondary headache, which is, oh my God, I changed something in my master data. Now I've got to go and ripple that through everything else. So how do I do that in Cosmos? Well, turns out we've got an ideal way of doing this, and it's called change feed. And change feed is basically kind of an API that's exposed by the Cosmos DB containers. You access it through our SDK, through the container resource that's within there. You listen to the container fundamentally, and then as changes happen, they're basically sent to a delegate, and then from that delegate, you can go and do something with the data that's within there. Whoops, did I miss something there? No, okay. So in our case, we're gonna listen to changes that happen to the product category container and also product tags. And when those changes happen, we're gonna catch it, we're gonna replicate it or update our product container within there, and then everything's gonna be in sync. So let me show you this demo. This one's definitely more interesting. And here we go. So I'm going to update my product category name within here. So here's update category. So I'm gonna grab a category. This is accessories, tires, and tubes. Now I'm gonna do something trivial here, and I'm gonna replace the and in that category name with an ampersand, okay? So I'm defining a new product category type here, just passing in the category ID, and category is a static name. And then here's my new name, accessories, tires, ampersand, tubes. And then I'm gonna call this function replace item async. This is another point operation. I'm gonna take a partition key and an ID, and then I'm gonna pass the new product category to that there. The second thing I wanna show you is change feed. Oh God, whatever. Within change feed, this is implemented in a very simple way. I'm gonna, change feed processor builder off my product category container within there, and then this is my delegate is input, and I'm gonna deserialize that as a product category type within there. So this thing runs and polls about every second. You can change that polling interval if you want, but that's what it runs by default. And then as new changes come in, it'll have multiples if there's multiples in there, right? Because this is an I read-only collection, so it's an enumerable collection that's coming in. And then as that happens, my code here is gonna iterate through all those changes, and then it's gonna call update product category name with my category ID and my new category name. So let me show you that. That's just a little further below. Here's my update product category name. And so I need to do a couple things here. I need to query for all products in that category, right? So select star from C where category ID equals that, pass my partition key. And then I'm gonna loop through all of those products. And I'm gonna change the category name to my new category name in there, and then call replace item async on each of the products within there. Okay, so there's all our code. Let's go and run it. So I'm gonna update product category name. So I've got print out the number of products. So I've got 11 products that are accessories, tires, and tubes. Let's update it. Now watch below. One change received. And I'll update it to ampersand in there. Let's go back. And I'm gonna print out the category in there. I've got 11 products that are accessories, tires, ampersand, tubes. Okay, in fact, I'll change this back in case that was too fast below. There it is, one change received. And it's updated. Now back to normal. It's in there. Okay? Is that cool? Did you like that? Okay, I got more. Damn, I'm done now, aren't I? It's top of the hour. Are you gonna let me go a little bit longer? 4? All right, let's do sales orders, right? Make them into JSON. I'm going to embed my details into that because that's good to embed it. That stuff gets access together, right? I need a partition key here. What's my operations? Create a sales order, list all sales orders, and query top 10 customers by sales order. Well, I'm going to make this really easy. This one is going to be our high concurrency operation, or at least the highest in this scenario here. So I'm going to use my customer ID as my partition key. And so every customer, all of their orders are going to be within a single logical partition within there. So that's going to be my partition key. Now, let's take a step back. Notice we have another container that has the same partition key, and that's the customer container. So could we mix those entities in the same container? Who thinks yes? Yeah, good, I'll give you all coasters. Yes, you absolutely can mix them all in the same containers. This is actually a benefit, a strength of a database like Cosmos. Cosmos doesn't enforce a schema, right? In a relational database, you gotta define your schema, right? Create table, blah, 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 right? Not necessary. That's all managed within your application. Your POCOs define your schema within there. And this is actually a best practice. When data shares similar access patterns, customer and their sales are generally accessed together, and they share the same partition key. In this case, it's customer ID. So I'm going to make some more changes here to my design. And I'm going to put both customers and their orders within the customer container. I'm going to now add customer ID to my customer entity. And then I'm going to add a new property, my type property. That thing's coming back. And I'm going to call sales orders are going to have a sales order constant in there, and customer is going to have customer constant, because I may want to query them separately within there, right? And so now for every customer that I've got within here, I've got a customer and a sales order, all their sales orders within there, right? And so here's my query. So select star from C, where C customer ID equals customer A, and C type equals sales order. So now I can get all their sales order back in partition within there. Okay. I'm going to try and get through the last of these. I'm sorry, this is going so long. I'm going to create a new customer, and I'm going to update their order total. The last thing I'm going to show you is transactions in here and denormalizing. In fact, let me show you this, and then I can do it all one big demo. So last thing I want to show you is this here. So my last thing, query number, top 10 customers by number of sales orders. This is actually a query that I can't run in Cosmos with this container that I've got. What I need to do is another technique, and that's called materializing aggregates. So in this case, I'm going to take sales order count, and I'm going to embed that as a new property within my customer record. And every time I create a new customer or a new sales order within here, I'm going to increment this amount and materialize it, save it back into my customer record here. Okay? So, yeah, so that's add a sales order, update the customer. Okay? So let me show you. Where are we? Create new order and update, create new customer and update total. So I'm going to get my customer ID here. That's my point read, right? Read item async within there. And then I'm going to do customer sales order plus plus. Okay, so I'm going to increment within there. And now I'm going to create a new sales order. And then I'm going to use this really cool feature called Transactional Batch. This is one of my favorite features in our SDK. But Cosmos, yeah, we're not relational, but we support transactions. The difference is that the transaction is scoped to, you guess it, a partition, a logical partition in this sense. And why do we do that? Because it all runs on the same machine. It's not a distributed transaction. I don't have to worry about locks on data. It's fast, right? And you're going to have predictable performance. So this is what we're going to use, is this transactional batch. And then we're going to create a new item. That's our sales order. And then we're going to call replace on our customer with the updated sales order total. Okay, so create a new order. Let's query for a customer and all their orders here first. We'll go pick on a single customer here. Okay, so this customer got 2 orders. All right, so here's my customer, Destiny Peterson again, the same one. And she's got 2 sales order. And I've got the customer record and both sales orders within here. By the way, one more thing I want to show you is how do I query for stuff when I've got multiple entities in the same container and I want to deserialize the thing? That's actually not too hard to do. Instead of deserializing data directly into a POCO, into a type, deserialize it into a dynamic type, and then as you iterate through the data, inspect the type property. Ooh, that's a customer. I'm going to deserialize that into my customer object. Ooh, that's a sales order. Deserialize that into that. Okay? Just wanted to show you. Okay, let's get back to here. Sorry, I'm so late. Create a new order. Create successful. Now I'm going to query that customer, and I'm going to show new order, and where is it? Sales order count is 3 now. Okay? All right. My very last slide. Sorry. Let me get to the model here. All right, you want the payoff? So, final design. 9 tables down to 4 containers here, but I can go one further. I can actually take the product category and product tags and make that into a single container. Because guess what? They share the same partition key, right? This is an excellent way of optimizing for storage cost in Cosmos. If you have like master data that's just looked up and referenced, or say things that hydrate your UI, stick them in a single container called meta or something like that, and then give them a type property so you can distinguish these things. You can quickly, easily query these things. And then if it's in a single container, you need one change feed instance, and you can manage your referential integrity to anywhere else in your database. Okay? That's it. So I went from 9 tables down to 3 containers. This thing is built to scale. Go anywhere. Key takeaways, I hope you got it. Here's a bunch of cool stuff. Thank you very much. Appreciate it. It's hard to stay within an hour, man, when I riff.
No, that was fine. No worries, man. Hey, we're going to have a 10-minute break.
Coaster.
What's happening to the stream now? For the people on the other side of the camera. This is, oh yeah, you just throw those coasters to everybody. That's nice. You can continue doing that while we are closing the stream here. So thank you for the audience in the stream. Here live we'll have a panel, and then we'll have food and drink. So we hope that you get food and drink at home too, or at work. Thank you for you there, and let's continue tomorrow. And here, 10-minute break. Let's come back 20 past.
Here, you throw the last one.
And thank you to Mark.